First of all, a sequence is a function that computes an ordered list. For example, if the average family spends $150 on groceries every week, then the function f of n equals 150n for n equals 1, 2, 3, 4, 5, and so on, and that would give us the sequence 150, 300, 450, 600, 750, sorry. This represents the amount of money spent on groceries after a certain number of weeks designated by the letter n. A sequence is a function that has a set of natural numbers or positive integers as its domain. The f of x notation is not used for sequences. Instead, what we write is a sub n equals f of n. N is used in the place of x to remind us that the domain is the set of natural numbers. The elements in the range are called the terms, and both the domain and range are ordered. A sub 1 is the first element, A sub 2 is the second, and so on. The general or nth term of the sequence is A sub n. The graph of a sequence A sub n is the graph of the discrete points in A sub n for n equals 1, 2, and 3. For example, notice the difference between these two graphs. The first one on the left is the graph of f of x equals 2x. It is a line. Every number that fits that is in that line. Fractions, decimals, negatives, and positives. The graph of a sub n equals 2n is not a line. Instead, it's a series of points. Notice 0 is not included. Notice that they're all positive. And again, we don't have fractions or decimals. We simply have the natural numbers, the positive integers being represented here. So we do not connect these dots into a line. That would be inappropriate. Sequence is often specified by giving a formula for the general term or the nth term. For example, we have a sub n equals n plus 1 over n plus 2. You're going to find the first four terms of the sequence. Very simply, all you're going to do is one at a time, you are going to replace the n's with the numbers 1 and get an answer, then 2, get an answer, 3, and then 4. Pause the recording, give this a try, and resume to check your answer. So you should have gotten 2/3 for the first term, 3/4 for the second, 4/5 for the third, and 5/6 for the fourth. A finite sequence has the finite set 1, 2, 3, and so forth until you get to n for some natural number n as its domain. In other words, like this example here, we're starting at 1 and we're ending at 10. There's a definite ending point to the domain, so it is finite. It does not continue forever. An infinite sequence has 1, 2, 3, and so on with no end. In other words, the set of all natural numbers as its domain. And an example would be 1, 2, 4, 8, 16, 32. The dots indicate that we are to continue in this manner basically forever. A convergent sequence is one whose terms get closer and closer to some real number. The sequence is said to converge to that number. For example, 1 over n. As n gets larger, a sub n approaches 0, so it converges to 0. A sequence that is not convergent is said to be divergent. For example, a sub n equals n squared. As n gets larger, the terms grow large without bound, and it does not approach any one number. So if you think about it, if you keep increasing n, your a sub n is going to get larger and larger and larger and larger. It's never going to approach a single number. In fact, it's going to approach infinity, but again, infinity is not a number, so it just continues to grow without stopping. A recursion formula or recursive definition defines a sequence by specifying the first few terms of the sequence and then uses a formula to specify the rest of the terms in terms of the preceding terms. In other words, it'll give you the start of the sequence and then it'll give you a formula that you can use those first few terms in to continue the pattern and find the rest of the sequence. For example, Let's find the first four terms of the sequence. We have a sub 1 equals 4, and a sub n is 2a to the n minus 1 plus 1. In other words, to get the next term, you multiply the one you just got by 2 and add 1. Pause this recording, give this a try, see if you can come up with the first four terms. Resume to check your answer. So we know that a sub 1 is 4. So a sub 2 is going to be 2 times 4 plus 1, which is 9. A sub 3 is going to be 2 times 9 plus 1, which is 19. And a sub 4 will be 2 times 19 plus 1, which is 39. Let's try another one. The winter moth population in thousands per acre in year n is modeled by a sub 1 equals 1, a sub n equals 2.5 a sub n minus 1 minus 0.19 a squared, a sub n minus 1 squared, for n is greater than or equal to 2. So start with, well, here's what you're going to do actually. You're going to give a table of values. You're going to find this from 1 through 10, and then you're going to graph the sequence. And remember, graphing a sequence is not a line, it's a set of points. Pause the recording, give this a try, and resume to check your answer. Okay, here's our table. And basically we just put in the numbers into the formula. They give us the first term, they give us a sub 1, and then from then on in you put the numbers into the formula. And this is actually the tables in two levels here. We have 1 through 6 at the top, and then we have 7 through 10 at the bottom. And the graph, it says, note that the population stabilizes near a value of 9.7 thousand insects per acre, which if you think about it with an example like this, a population, there comes a time when the population just can't grow anymore because of its environment. So this actually makes a lot of sense. S sub n is the sum of the first n terms of a sequence. So when you have a sequence, if you were to add all the terms together, get the sum, and that is symbolized by S sub n. We use the Greek letter sigma to indicate a sum. The sigma notation, right there that you see, we've got the sigma, on the top is an n, on the bottom is I equals 1, and then we have a sub I. What that means is you need to add the terms a sub I, beginning with the first term and ending with the nth term. So the bottom number tells you which term to start with, the top number tells you which term to finish with, and the I is called the index of summation. So a finite series is an expression of the form S sub n equals a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n, and there's the symbol for it using sigma notation. And the infinite series looks like what you see here. Instead of having a definite stopping point at the top of the sigma, we have the symbol for infinity. So remember, a sequence is the listing of the numbers. A series is when you add all of those numbers together. Okay, here's an example. You're going to write the term for each series and then add them up if you can. Pause the recording, give it a try, and resume to check your answer. Okay, so the first one tells us that we're going to add a sub j from j equals 3 to j equals 6. We really don't know what a is, so we're just going to replace the j with the subscript. So a sub 3 plus a sub 4 plus a sub 5 plus a sub 6. For part B, we actually have an equation. So I is going to be 1, 2, and 3. We start at 1, we end at 3. X sub 1 is going to be 2. X sub 2 is going to be 4, and x sub 3 will be 6. And we substitute those values in and add them together, and we get 66. And then finally, I is 1, 2, 3, and 4, because that's our starting and ending. F of x is x squared, so x sub 1 is 0, x sub 2 is 2, and x sub 3 is 4, and x sub 4 is 6. And when we put all of those in there, we get x sub 1 squared delta x plus x sub 2 squared delta x plus x sub 3 squared delta x plus x sub 4 squared delta x And then when we square the values of x, we get, and put in that delta x is 2, we get what you see there. We add them up and get 112. A few properties of summations. The first one tells us that a C here is a constant, so it's a number. So if you were trying to add the sequence from 1 to whatever of a constant, then you really just multiply that top number, that n, by the constant, and that's all you do. Because what you're really doing is just adding that number to itself however many times n tells you to. Part B tells us when we have a constant that's multiplied by a variable, we can pull that out front. Not a big surprise here, we're really just using factoring out. That's all we're doing. We're kind of reversing our distributive property. Part C tells us that when we have two variables we're adding together and taking the sum of that, we can actually split it up and do the sum of one plus the sum of the other. And Part D lets us do the same thing but with subtraction. Here are a few more rules. When you want to add a sequence, of numbers together, there's a really easy trick to it. If it's just a number itself, like you want to add the numbers from 1 through 100. Okay, there's a really quick trick for that. What you do is you multiply 100, or n, whatever that nth term is, whatever that top number is, times that top number plus 1 over 2. So in the case of adding the numbers 1 through 100, you're going to multiply 100 times 101, and you're going to divide by 2. For the second one, if you have a square, the formula is a little bit different, a little more complicated. This time you've got n times n plus 1 times 2n plus 1 over 6. But that will add a bunch of numbers, series of numbers that have been squared. And then cubed, you have a different formula there, n squared times n plus 1 squared over 4. So let's use those properties to evaluate these numbers, or these summations. Pause the recording, give it a try, and resume to check your answer. Okay, this first one is just when you're adding a constant. Basically, what we're saying is add 5 to itself 40 times. Well, you might as well do 40 times 5, which is 200. Part B tells us we use the rule that we can pull the 2 out front, and then we use the rule for adding just a variable, just the variable, from 1 to 22, which would be 22 times 22 plus 1 over 2. And working out that, you get 506. C, we're going to put together the rules for 3 things here. We're going to pull the subtraction apart, then we're going to pull the 2 out in front of the summation with the I squared, and we're also going to use our formula for adding up I squared. And putting all that together, you should get 1988. Okay, the rest of this is extra practice. Pause the recording as you go through these and resume to check your answers.